Hey everybody, I wanted to talk to you guys about a new project that I've been working on. Over the last few weeks, I have been speaking with uh, individuals who work in the MSP sector, both with engineers in the NOC and AI engineers who are building the backend infrastructure. And the MSP industry is still pretty fledgling and it's learning on the job and uh, it is in the process of devising the right strategy to incorporate AI into their frameworks. And in the current agentic revolution, MSPs are still in the process of, bridging the gap between robust AI-driven agentic solutions and the right security guardrails that will prevent, AI agents going completely haywire. But this these conversations bring up a really interesting point and interesting wrinkle that is worth discussing in detail. How do we make sure that the agentic solutions that we have is not only sophisticated and it's not only something that gets the job done, but at the same time, it is secure, it is well architected, it is cost effective, but more importantly, it is extremely reliable. Because the one thing that we cannot lose as folks who work in the MSP sector with our clients is the trust of our clients, because that means a lot to us. And that is the through line that connects the tech world to the business world. And that is really what is at the forefront of every relationship that we as an MSP at Red have with our clients and multiple other MSPs have with their clients. So even with the incorporation of AI, there has to be a deliberation process to make sure that the solutions that we have in place, they're extremely reliable. And with that in mind, I actually want to talk to you about this very interesting paper that I read a week ago. It's called On Reliability Limits of LLM-Based Multi-Agent Planning. It's written by Professor David Sinchi-Levy, Ruching Ao, and Xiang Bao. And there are three really interesting facets of this paper that I found extremely interesting. So this is the diagram that I have to sort of explain to you in, uh, I would say, uh, as cogently as I can. Uh, the paper is extremely well written. It's very mathematics heavy, and it really pushes you to, think about uh, agentic capabilities from a different perspective. And I think that's what great research does all the time. And so let's start with the first aspect of the paper that I found very interesting. The way we understand multi-agent frameworks today is this linear chain wherein you have the planner agent that does all the planning. It hands off that information to the first actor agent that is responsible for doing a specific part of the entire goal. And then that particular agent hands off the information to a subsequent agent. And then this chain continues. And so the first aspect of this paper that the authors bring up is how do you justify the presence of a, a multi-agent framework with a linear information flow from the planner agent all the way to the final actor? One of the things that's very important here is to understand the fact that we can only justify the presence of an agent if that particular agent is bringing in new information that only it has access to and the other agents don't have access to. That is how we will justify the presence of that specific agent. If that particular agent has the same access to the same information that its predecessor has, then the novelty factor that it's bringing to the table, it's completely null and void. And so you cannot justify why you cannot solve the exact problem with just having one agent instead of a multiplicity of agents. So that is the first facet of the paper that I found very interesting. What is the novelty in terms of information access that a particular agent brings to the table? So that's number one. Number two, and the second facet that is really interesting about the paper is how the author sort of articulate a reliability framework that we can use in a multi-agent framework. And here the researchers use uh, the intuition from Bayesian probability, where they essentially posited that the certainty that an agent has, given access to certain information, can be posited in terms of this Bayesian probability, which is a probability distribution that articulates the confidence that an agent has on the solution that it has framed, given it has access to a certain information A. And so the higher the confidence of that agent on its given solution, the greater the reliability that we can ascribe to the solution that the agent has formulated. So that's number two. And the final point that is really intricately tied to the second point is if you have a multi-agent framework that you have justified and that is in place, but if you see there is a proportionate catering of confidence from one agent to the next. So let's just say that the distribution of the first agent demonstrates a 76% confidence. The confidence demonstrated by the second agent is 70%, and then finally by the third agent is 64%. And so you see this proportionate catering of confidence from one agent to the next. So the way the researchers explain that, they explain this facet is the decrease in the confidence of agents in the solution that they're formulating can be proportionately ascribed to the loss in information during the handoff from one agent to the next. And this particular loss in information can be expressed using KL divergence. KL divergence. So they use so KL divergence is a concept in machine learning where we calculate the disparity in two distributions. And the higher the KL value, the higher there is a disparity between two distributions. It's also a technique that we use in language model distillation when we are training a smaller model or a student model on a greater, on a bigger, on the data that is given to the bigger feature model. Uh, so we use scale divergence to think about the loss of information from one agent to the next. And the researchers say that that particular loss in information is proportionate to the catering of the confidence that the agents demonstrate in performing a certain task. Now, think about one thing. Now, this was the aspect of the research that I wanted to speak to you about that I found really fascinating. But how does this extrapolate to a real MSP use case? So think about having a agentic workflow automating parts of your MSP triage. Now, this is where the trust factor becomes really important because let's assume we are dealing with security alerts. There are different kinds of security alerts. There are some security alerts which are extremely convoluted that requires the active involvement of an individual, of an engineer in the process. On the other hand, there are certain security alerts that are pretty rudimentary. And it's better if an agent can go into the system, parse through the issue, and actually solve that issue without the involvement of the human. And therefore, I think this particular use case opens up opportunities to think about reliability from a different perspective. So think about two entities here. Uh, on the one hand, we have the risk of automation. So when you're involving an agent and when you're giving it access to your system, you're incurring certain risks because it will be going inside your system and it will be automating a certain part of your workflow. On the other hand, if a human engineer works on a specific security alert, there's human cost involved. If the issue is rudimentary, the engineer could be just suiting that job to an AI agent, and during that time, the engineer could be doing something more productive. So keeping that in mind, let's actually take a look at Let's actually take a look at a real world MSP triage intelligence such scenario where we have I have basically created some examples here so that I can take you through and explain to you what I mean by that. So in the, for example, give me a second. Okay, so we choose Staten Island LLC. False positive noise. We have our target asset, and let's just say that we are giving description as this. Okay, so when I submit it off, now it the pipeline is in progress. Now the agent reliability pipeline is running, and if I view this request in queue, this is on track. Now, as you can see here, uh, the in this particular case, the agent is saying with 100% certainty that that it's a false positive issue, as and it has basically determined that the cost of human involvement will be much higher than the automation risk. And so in this case, because it has successfully diagnosed the issue with 100% certainty, we can say that in this particular case, the automation risk is significantly much lower than the human cost. Let's take another example. Let's take Midtown CPA Partners. We have suspicious different credentials. I, right, submit. And then let's just say that what our agentic pipeline gives to us. So based on this particular information, we have it in the queue. And so this is where you have, now as you can see here, we have our risk of automation as 0.15 and our human involvement cost as 0.21. Now, unlike our last example, this particular example, uh, in this particular example, we have pretty neck and neck in terms of the automation risk and human involvement. Now, you can go sort of both ways in this case. You can say that, okay, the automation risk has a lower score, so maybe we can try and rely on, uh, we can rely on our agent, but it also indicates that the human cost is not too high. So maybe we should try and involve the human in one or two situations, but then going forward, we can let the agent do it. So this is another example. Now let's actually go to a different one. So we have Astoria Financial. This is the asset. All right, let's see what our pipeline gives us. So the tracking pipeline is currently running. And finally, the decision has been made. Let us view in queue. Okay, so this time you can see the human cost is definitely much higher than the automation risk. And so this is also one of the scenarios where, uh, you know, uh, you can rely on uh, your basically agent to go ahead and do the task. Definitely, take the right decision and see and definitely sort of evaluate uh, what decision the agent really takes, because once you evaluate your agent's decision multiple times, you can come to certain a certain conclusion. Now, as you can see over here, that the decision has, so it's saying that immediately conduct a detailed investigation of the files, exported and verify if the data and the exfiltration occurred, interview the departing privileged employee. Uh, so the pipeline has routed to an analyst in this particular case. Now, if you can see here, ready for save mock auto action. So here it took an auto action, and here it goes to escalate to an analyst in the scenario. That's very surprising given the fact that your risk of automation is much lower than your human cost. The RH in this example is clocking around 0.210. But this is a reliable framework that one can leverage to sort of really understand how much credence should we give to our agentic framework. And what the researchers have done really well is giving the agent an opportunity to produce its own confidence of its own performance. And that confidence helps us understand how reliable the agent is in the first place. And that is really a good framework to design and develop our agents, so that we are not only taking its answers that it is giving, we are actually determining whether or not it is giving us the information to, or whether or not it has confidence in its ability to solve a specific problem that will help us in MSPs devise a policy that would help uh, our framework in the long run to solve specific problems. So this is something that obviously, in the future, I would be fine tuning it a little more, maybe, adding a few more points to this. Currently, the architecture that I have, if I will show you how it looks like, let me quickly go ahead and take the diagram. So this is the current architecture. So as you can see, uh, basically this reliability aware intelligence pipeline is the one that is using an OpenAI driven model to basically see whether or not it is going to escalate it to a human analyst, or it is going to basically take auto action. And that really depends on the disparity between the risk of automation and the human cost involved. And as you can see here, we are using the KL distortion monitor to check the posteriors between the baseline and the classifier. And we are calculating the risk of automation by taking the subtraction from one of the maximum of the posterior that is calculated in the probability distribution of the agent. So uh, Obviously, this is still a POC. It's a fledgling, uh, you know, framework that I want to fine tune in the future because I see a lot of scope in, developing frameworks that will help agents become more reliable in, triage workflows, and it will, at the end of the day, give insurmountable value to MSPs. So thank you so much, guys, for uh, being with me as I explained you uh, the entirety of the project that I've been working on. Thank you so much.